So hi everyone. So my name is Daniel Hauschild. I'm from Imagely, streaming live from Germany actually. So it's pretty late here. I hope you're all still awake in your time zone. So maybe some context before we start. Imagely itself is a creator of SDKs for image editing, much like from Adobe Photoshop, etc. But we provide solutions for the web and other platforms which can be white labeled and used. And in this context, we try more and more to use AI, and in this case, neural networks to improve editing experiences. And today I brought an example where we used the ONNX runtime or ONNX in general to provide editing capabilities in the browser. More specifically, we are talking about background removal, which is a common tool for editing. Basically, many years ago, it started to be useful, and everybody was using server-based versions to do that. But now, since the runtimes and also the web improved so much, we can start leveraging it directly in the browser on the client without any server connection. And that's what I will talk about today, and also mention the issues that come with that. So, like I said, we are basically moving every computation to the client, which has a lot of advantages for us. Because first of all, we don't need to run any servers, which is a cost improvement. Second of all, there's also, you can imagine that all editing is happening in the browser. That means all image data is also in the browser. If we leverage servers, we have to upload, encode all the images, wait for the upload, process the image and send it back, and the experience will suffer under that. Also, with our bigger enterprises, there are some issues when we provide servers because depending on where they are located, they might have issues with data protection policies, and especially in Europe, these are pretty strong. So best case, everything can happen in the client, and only we need servers for more advanced stuff. So what we did is we started with a typical PyTorch implementation of our background removal network. And now the problems began. So actually, the thing is, if you start going into the web, there are several issues which you will encounter. So for sure, it's how to run it first, and how to run it fast, and how to transfer it fast. I can tell you why I'm talking about the transfer or download part also. So first of all, we are using, or we realized that using the ONNX runtime helped us a lot, advancing also performance. Recently with 1.16, I guess, they introduced also web GPU support. Before that, we were solely relying on WebAssembly or other technologies to run multi-threaded in the browser, which I can tell you still works, but the performance is not near real time. Okay, so let's first talk again about feasibility of running things in the browser. So obviously everything is about execution performance, which is everywhere the same. So if you talk about interactive editing, we are dealing in sub-second ranges. If you go real time, you are 60 seconds, 60 frames per second. But we are always thinking like 100 milliseconds, or there are certain ranges of time to 200 are okay for a user to not get bored or wait for things. However, what we also realized with neural networks, we got into another problem, and the problem is the sheer size of neural networks. So in general, we are not talking about tens of megabytes, but more hundreds of megabytes to gigabytes. In our case specifically, we are talking about a pure network in safe tensor format was like 168 megabytes, which is not much in LLM terms, but if you have to download it all, it will take some time, and even that first time experience would take longer probably than the editing. So especially in the first time experience, you're adding problems. And what you're seeing here in the graph is just rough estimates for like 100 megabytes, or not 100, but 80 megabytes. I'll tell you why later. And typical networks and how long it will take. And we can see with a typical 1 gigabit per second network, maybe you have a faster one, but you're already in the range from 100 milliseconds to 1,000 milliseconds or a second. And if you go slower, like 100 megabytes, which would be my current connection, actually, it would go to more like 10 seconds to just download the network. So you can imagine, so first time you use the tool, you run into the problem of having to download it first. And for users, it's always like a blocker. The second thing that also becomes a big part is then the session initialization time. So the reason why is the same with the download. So even when you download it once and you may have cached it in the browser or stored it in local storage or something, some technology of the browser, you still have to load the weights into the specific, let's say, instance of the runtime, and this also takes some time. And here you can see a few benchmarks of the ONNX runtime running on a MacBook Pro with 60 cores, so pretty modern hardware, so it should be pretty fast, already not something that everybody has. And here you can see two comparisons. First, there's the CPU or WebAssembly based execution provider of ONNX runtime. And we benchmarked it against the FP32 or 32-bit floating point or 16-bit floating point. And it turns out this is already around 320 milliseconds for both. So already, again, pretty much. For the web GPU initialization instead, it's FP32 is like 400 milliseconds and FP16 is way faster, around 200 milliseconds. So we are not developers of the runtime itself because they will be, Microsoft or someone will be probably be better at explaining why. My best guess is that FP16 half the size and the upload bandwidth to the GPU is basically what's important here. And okay, I didn't mention it, but it's probably obvious for you. It's that FP16 is just the 16-bit floating point, let's say, optimized version of the model. Just for you to know, some of you will ask why I'm not using some quantization like even smaller, like 8-bit. But the problem is that, especially in image-based things, quantization largely influences the quality of the output, and it's visible directly in artifacts, or let's say wrong masks. If you talk about background removal, we are talking about masking the image, and if you quantize it, the mask gets worse, and then you don't have a result which is usable. So we are here, at least for now, stuck with 16-bit. So, and now comes for us the important part and why these recent developments of WebGPU were really, really interesting to us. So here you have some numbers of us, again, benchmarking on the same laptop as before, benchmarking the performance. And when we started, let's say almost a year ago, we started with the WASM edition or WASM version. And if you can see the single thread WASM version, so no threads, no SEMD enabled, just pure one-threaded CPU. It took like 55 seconds to basically remove the background of one image, which is pretty long. Then again, it's already speeded up a lot when you activate SEMD and also have 16 cores on your laptop. Then it's sped up to 2.3 seconds, which was the first time. That's actually the time when we released it first time, which brought it down to 2.3 seconds, up to, on Commodity Hyper, to 10 seconds from my experience. So this was already a speed up of 24x, which was pretty great and made it feasible the first time to make it useful for in-browser background removal. However, then a few months ago, so we started experimenting with WebGPU, and here you see those times. So we brought it over to the WebGPU execution provider, had to fix some stuff and of unsupported operators. And when we got it running, we saw a large improvement actually. So we saw that the FP32 model only took 120 milliseconds to execute, which is already a really big speed up to the single-threaded version of 366 times, or the FP16 is even faster, probably due to the GPU hardware, which is supporting FP16 compared maybe to the CPU hardware, like a 550 times speed up. So now we are in a range now with the execution time of 1/10 of a second, which makes it really, really useful now and the experience really great. The thing, however, is, as I mentioned before, that for us, so we have a consumer product where people, which is used, not a consumer product, we have a product which is used in scenarios where people start editing things only one time. Imagine our software being used in stores for, let's say, creating photo books or creating t-shirts, or even for marketeers adopting designs to ship to multi-channel marketing. But the problem is that those people mostly not use the editor every day. So every time they start it up, they will have to download the neural network, etc. So what you can see here is one of our biggest problems actually in user experience is basically now the startup time. Now we solve basically the execution time, And now the startup time is again, and the download time, a problem. So because in comparison, those are now becoming the bigger issues. However, as you mentioned, downloading can be cached. However, session initialization cannot yet be cached perfectly because for every laptop, etc., the WebGPU shaders will be recompiled. And also, for now at least, there's no proper way to store or cache the resulting optimized network in the browser and the WebGPU shaders for this specific runtime, for this specific network of one specific ONNX network. So for those who want to see how this all works in the browser, we have open sourced the whole background removal library for JavaScript. It also got some traction, like 5K stars on GitHub over 1 year, because we solved the problem, I guess, for many people, because it saves a lot of money, to be fair. And feel free to check it out and leave feedback if you have any input how to do it better. So if we still have some time, I also brought a quick demo. So I would switch over and show a short demonstration. So here you see our editor in action, and the background removal is basically in there. And you will see that the first time execution will take some time because it's in the background downloading the model and also having to initialize the session. And then here you see it seems like a pretty fast network today, and it worked quite well in a second something. However, if you do more consecutive calls of that, you will realize it's much faster. And this experience is what we are striving for. And like I said, for our customers, etc., this is a huge leap because, and that's why we also really like that ONNX runtime is going to more and more on-device things, because that enables a lot of user interactions, a lot of data safety, and what I mentioned in the beginning. So, okay, that's it from my side so far. Thank you.
So every time somebody has to download the model from the web, essentially, is that more expensive than having every inference go to a server instead? Like, what's the cost difference of downloading a model every time versus just sending those inferences out and keeping it on the server side?
Okay, so the thing is, if you have multiple users, I have a bad echo, sorry. The first time everybody downloads it gets cached. So this costs something. However, if you do it then 10 times or reopen the browser, you don't have to download the network anymore. So it's a really first time usage. This is comparable, so this is much better than upload. So you can imagine all the images, if you have 3K, 4K images and 5 to 6 megabytes each, putting it up to the server with every image, then there is a point where it gets much cheaper. Also remember that serving the model, so it's cheaper from the runtime, but also the cost, because one is just, let's say, S3 egress costs, and the other will be some GPU server execution costs, which is definitely more expensive. Thank you. See you.